Physical science students, this is our next unit, chemical reactions and the law of conservation of mass. So we're going to get into the different chemical reactions and kind of can't physically play with them this year, but we can look at them, check them out. They're some neat ones. Question I would ask you, if you found the mass of a pile of firewood to be 5 kilograms, you put that on a scale and determine that the mass of the wood is 5 kilograms, and you used firewood in the campfire, got it going, okay, got it burning, put all 5 kilograms in, and then you measured the mass afterwards of the ash, and you saw that the ash laying there was 3.8 kilograms. If your teacher were to tell you that according to the law of conservation of mass, a chemical reaction cannot destroy or create mass, but just transform it, and you're looking at this and you said, okay, well, I had 5 kilograms of firewood, and now I'm looking at just under 4 kilograms of ash. So where does the other 1.2 kilograms of mass go? Okay, and we're going to learn some terms coming up here. One is reactant and the other one is product. So in this case, the reactant would be the firewood, the product would be the ash, but I'm leaving something out, right? If you think about it, I'm leaving out the smoke, right? The smoke that blew away. 1.2 kilograms of it in this case, okay? All right, this is a man who first came up with the concept of the law of conservation of mass.
This way, please, gentlemen. Monsieur, it is my great ambition to demonstrate that nature is a closed system. That in any transformation, no amount of matter, no mass, is ever lost and none is gained. Over here, please. This precise amount of water is heated to steam. This steam is brought into contact with a red-hot iron barrel embedded in the coals. From this end, we cool the steam, but interestingly, we collect less water than we started with. So clearly, we lose a certain amount of water. However, we also collect a gas, and the weight of the iron barrel increases. Now, when we combine these two increases, the new weight of the iron barrel and the gas we have collected, they are exactly equal to the weight of the lost water.
But is it atmospheric air, Monsieur Lavoisier?
Now, because I am measuring it to the very last grain, I can see that it is lighter than the air around us, and moreover, it is flammable. Voila.
Water is made out of hydrogen and oxygen. So what he had done is get the oxygen to stick to the inside of a red-hot iron rifle barrel. He was basically just making rust, which is oxygen and iron, but he was making the rust really quickly. Now that left the hydrogen, what he called combustible air, and that was just floating around as a gas. No mass had been lost, it had merely been transformed, and now he wanted to transform it all back into water.
This is only the beginning. In the next few months, I hope to demonstrate that I can recombine this combustible air with vital air and transform them both back into water. I will recreate exactly the same amount of water that was lost here in this process. It is my hope to complete the cycle, water into gas, into water, and not a drop lost.
For a long time, Lavoisier had suspected that the exact amount of matter, the mass, involved in any transformation was always conserved. But to prove this, he had to perform thousands of experiments, and he had to do the measurements with incredible accuracy. That's where his great wealth from being a tax collector came in. He could afford to commission the most sensitive instruments ever built. He became obsessed with accuracy.
Expose this pussy.
Okay, so that's
This way, please, gentlemen.
oops. Sorry, guys. Okay, so that's sort of the original, the first kind of inception of the law of conservation of mass. Now, so to break it down, if you look at it, like just take this pickup truck, which is going through a real slow chemical reaction. It's slowly becoming rusty. And if you were to take all the rust that's generated over time as it decays, and it's going to flake off and fall to the ground and break down. But if you could collect all of it, at the end of the day, you'd have the weight of the original pickup truck. Some things that I'd like to just sketch in your notes, some symbols that we're going to use as we go through chemical reactions and writing chemical reactions. One of them is that little S for solid. Sketch that down, that's what it stands for. You'll see it a lot. The little L for liquid, the G for gas, the AQ for aqueous. Also, instead of an equal sign, you're going to see an arrow. And everything to the left of the arrow is going to be what's called the reactant, and everything to the right of the arrow is going to be the product of the chemical reaction. Okay, so for example, reactant, that's R, and P, that's product. So in the case of dynamite, you'd have a stick of dynamite, and you catalyze it, and that's a word we're going to play with too, catalyst, by lighting it on fire. And then the resulting reaction of the nitroglycerin contained within the dynamite stick, that blow up, that's going to be the product. So reactant on the left, product on the right. Okay, we're going to go over a couple of the different types of chemical reaction. The first one is characterized by the letter A plus B, and then you draw that arrow for chemical reaction, and AB. So copy that down. A plus B, the arrow for chemical reaction, and then AB. Okay, this is what's called a synthesis reaction. You're going to want to copy that down as well. And you can pause this, I'm going kind of quickly. The synthesis reaction. So to synthesize means to make. So A plus B becomes AB. And the example down below here would be the gas hydrogen plus the gas oxygen becomes water. I'll show you an example, a famous example. It was in a movie of this, and if we have time, we'll keep going.
square meters of soil, but every cubic meter of soil requires 40 liters of water to be farmable. So I gotta make a lot more water. Good thing is I know the recipe. You take hydrogen, you add oxygen, you burn. Now I have hundreds of liters of unused hydrogen at the MDB.
if I run the hydrazine over an iridium catalyst, it'll separate into N2 and H2. And then if I just direct the hydrogen into a small area and burn it. Luckily, in the history of humanity, nothing bad has ever happened from lighting hydrogen on fire. NASA hates fire because of the whole fire makes everybody die in space thing. So everything they sent us up here with is flame retardant, with the notable exception of Martinez's personal items. I am sorry, Martinez, but if you didn't want me to go through your stuff, you shouldn't have left me for dead on a desolate planet. By the way, I'm figuring you're going to be fine with this, given my present situation. Up. Best guess, I forgot to account for the excess oxygen. I'm gonna get back to work here just as soon as my ears stop ringing.
Yeah, so that's a chemical reaction that eventually in that movie, The Martian, he is able to successfully create water. The next type of chemical reaction, and you're going to want to copy this down, is AB becomes A plus B. This, just like anything rotting or breaking apart, is what's called decomposition. So first reaction was synthesis. This one's called a decomposition. In the example that I'm giving you below, water using something called electrolysis breaks into hydrogen and oxygen. Here's a video of that.
I absolutely love teaching. I just wish I had more time to prepare fun lessons, especially...
What is electrolysis? No, not the thing that removes the hair on your chinny chin chin. It's the thing that might help cars run. Hey guys, Julia here for D News. At its most basic level, electrolysis is the splitting of water into hydrogen and oxygen by an electric current. Usually this current is created by placing two electrodes in the water. Typically, these electrodes are made of different metals, so one acts as an anode and the other as a cathode. The cathode is where the electric current flows from, and the anode is where it flows to. One is considered positive while the other is negative. If you've ever taken a chemistry class, you might know that water is H2O, which means it's made up of two hydrogen atoms and one oxygen. But these atoms are covalently bonded, which means they share electrons. When electricity splits that bond, oxygen gets a little sneaky and steals an electron from the hydrogen in the process. So then these molecules become charged and become attracted by either the cathode or the anode. Despite what Hollywood would have you believe, pure water is a pretty poor conductor of electricity. So usually an electrolyte is added to the water, like lithium or sodium. Electrolytes have more ions that allow the electrical energy to move through them. When water is broken up, the oxygen might bind with things like the sodium, but the hydrogen bonds with itself and forms a hydrogen gas. But why would you do this? What's the point besides having fun in chemistry class? Well, to fuel things. It's a pretty combustible element, so it could be a great fuel source. Have you heard of hydrogen fuel cells? Well, where do you think they get that hydrogen from? Hydrogen is in a lot of things. It's everywhere. Like 75% of mass in the universe is hydrogen. That's a lot. But hydrogen is kind of a little frisky molecule. It likes binding with other molecules. So if you want to get hydrogen by itself, you got to be like a little homewrecker and get all up in that and break it up. Sometimes by using electricity. Once you break up water, you can store that hydrogen and later use it as fuel. Michael Faraday first discovered the phenomenon of electrolysis back in 1834. So why hasn't it been like a thing in the past century? It's those dang electrodes. A lot of materials corrode as soon as the current is applied, so they don't really last in the long term. So you want an anode material that is resistant to damage from oxidation and a cathode material that is resistant to damage from reduction, but both need to be capable of the appropriate reaction. Luckily, scientists are working on it. In one study published in the journal Advanced Materials, they used a cobalt coating that worked for both. The researchers found that it's cheaper than other materials and maybe even scalable. They think it could even be scaled up to a huge industrial size. I mean, imagine whole towns being powered by it.